the sky opens wide, stretching into a quiet depth where most of reality hides from view. Less than 5% of the universe is the stuff we can see. The rest shapes us from the dark. High-energy cosmic rays, born in supernovae and near black holes, pass through our bodies every second, leaving faint marks on life and maybe even climate. In the quantum realm, reality shows up as probabilities until an observation fixes an outcome, while entangled particles stay linked across any distance. On the larger scales, dark matter gives galaxies their scaffolding, and dark energy drives the universe to expand faster and faster. If this kind of clear, calm exploration helps, consider a gentle like and subscribe. Tonight, we follow the hidden threads from particles passing through you to forces shaping galaxies, and watch the unseen right reality. Imagine, for a quiet moment, that you could see everything that is truly present around you. Not only the solid chair, the walls, and the soft glow of visible light, but the full scene that physics says is here all the time. You would notice subatomic flickers in the space between your atoms, tiny particles appearing and fading so quickly that they barely count as things at all. You would sense neutrinos, particles born in the sun's core, moving through you by the trillions every second. Neutrinos almost never interact, so they pass like gentle shadows. You would feel faint tides in space itself as gravitational waves from far-off black holes stretch and compress the distance between your bones. Radio waves would wash through the room, carrying music, calls, and data streams on many frequencies at once. Under that, quantum fields would roll and jitter. These fields fill all of space. Their small changes decide which short-lived virtual particles can spark into existence for a moment and then return to the background. Threaded through it all would be dark matter, an unseen framework that does not shine, but still adds gravity, passing through your body as if you were made of air. Empty space would not feel empty. It would look like a calm surface with hidden motion, the vacuum itself buzzing with energy, while space-time ripples as if a distant pebble had touched a still pond. The world you know, the part made of atoms and light, adds up to less than 5% of the universe. The other 95% runs on rules that seem strange compared with everyday life, yet those rules guide the shape of galaxies and the pace of cosmic expansion. This invisible part is not somewhere else. It shares the same space you stand in. It moves through your breath and sits beneath your thoughts. To understand what it means to exist here, we have to look beyond the shortcuts our senses use and accept a quieter, wider picture. A good place to begin is where the hidden cosmos meets you most directly. Particles that have crossed vast distances only to pass through you without a sound. Right now, about one cosmic ray particle hits your body every second. A cosmic ray is not a soft breeze of ordinary matter. Most are bare atomic nuclei, often protons flying at speeds very close to the speed of light. Their energies are huge compared with anything we can make on Earth. Some reach more kinetic energy than a baseball thrown at highway speed, yet that energy is packed into something far smaller than a grain of dust. When these particles hit the upper air, they crash into atoms and make a chain reaction. The first strike produces new particles, which hit more atoms, which make more particles, and a shower spreads downward. Among the fragments are muons, heavier cousins of the electron that live long enough to reach the ground. On average, roughly 10,000 muons pass through each square meter every minute. Many go through you. You do not feel them because, like neutrinos, they interact only rarely and usually leave no trace that your nerves can detect. Where do such powerful particles come from? Some begin in the end stages of massive stars. When a heavy star runs out of fuel, its core collapses in less than a heartbeat. The outer layers rebound and race outward as a supernova. For a short time, that single event can shine brighter than a whole galaxy. The blast drives shockwaves into surrounding gas at thousands of kilometers per second. Charged particles bounce back and forth across those shock fronts, gaining energy each time, like a child gaining speed on a swing when a push arrives at just the right moment. This process, called shock acceleration, turns the debris of a dying star into a natural particle accelerator. The particles that escape become cosmic rays and start long, winding trips across the galaxy. They may wander for millions of years, bent by magnetic fields, before a few finally reach our atmosphere and continue their quiet path through you. Other sources push energies even higher. At the hearts of many galaxies sit supermassive black holes. Gas and dust swirl toward these giants in a thin, hot disk. Friction and magnetic fields make the disk heat to extreme temperatures and twist the paths of charged particles into tight spirals. Some particles find themselves on magnetic tracks that fling them outward at near light speed, sometimes in narrow jets. To such a particle, time slows down because of relativity. From our view, it may take millions or billions of years to cross intergalactic space. From the particle's own point of view, if it had one, the trip could seem to pass in moments. The very highest energy cosmic rays are still a deep puzzle. In 1991, instruments in Utah recorded a single particle with a shocking amount of energy, so high that scientists first suspected an error. The energy was on the scale of a baseball thrown at about 60 miles per hour, packed into one atomic nucleus. Physics predicts a limit on how far such particles can travel. On the way to us, they should collide with the low-energy photons of the cosmic microwave background, the afterglow of the Big Bang, and lose much of their energy. This limit, known as the GZK cutoff, suggests that ultra-energetic particles should either be born relatively nearby in cosmic terms or arrive weakened. Yet we detect events that hint at great distances or at sources and processes more extreme than our standard picture allows. To explain these outliers, researchers consider ideas from the edges of known physics. One idea involves cosmic strings, thin, line-like defects in space-time that could be leftovers from the universe's earliest fractions of a second. If they exist, they would be incredibly narrow and dense, stretching across huge distances like nearly invisible threads. When such strings kink, cross, or snap, they could release bursts of energy strong enough to fling particles to the observed extremes. This remains hypothetical, but it offers a clean way to store and release enormous energy without bright fireworks we would already have seen. Another idea looks to primordial black holes. These would not come from dead stars, but from dense regions in the young universe. Over time, very small black holes should slowly lose mass through a quantum process called Hawking radiation, leaking energy until they finally evaporate. The last moments would be fast and violent, with a spike of high-energy particles. If some primordial black holes still linger and are now reaching their final phase, they could seed the sky with extremely energetic cosmic rays. Even without reaching such extremes, ordinary cosmic rays matter to life and to our planet. When they strike the atmosphere, the secondary particles can help seed tiny droplets that become clouds. The effect is complex and depends on many factors, but it is one way the sky's invisible traffic may link space weather to Earth's weather. On longer timescales, cosmic rays can change DNA by causing rare damage in cells. Most changes are corrected, and the rates are small compared with other sources of mutation. Yet, over millions of years, they add a background rhythm to evolution. Air travelers and people living at high altitude receive a bit more exposure. Electronics sometimes record sudden bit flips from passing particles. Deep underground detectors count muons and neutrinos to study the sun and distant explosions. All of this happens quietly while daily life carries on. It helps to remember a few simple definitions as we go. A neutrino is a nearly massless particle that interacts through the weak nuclear force, which is why it passes through matter so easily. A muon is like a heavy electron. It decays in a tiny fraction of a second, but can still reach the ground from high in the atmosphere because it moves so fast that time for it is slowed by relativity. A quantum field is a kind of background that fills all of space. Particles are excitations of these fields, like small ripples on a broad surface. Dark matter is unseen mass that pulls with gravity but does not glow or absorb light in ways we can detect directly. Gravitational waves are ripples in space-time, made when massive objects like black holes move and merge. Each of these ideas has been tested in different ways, from detectors buried in ice to telescopes in orbit, and together they draw a picture of a universe that is busy even when it looks still. Stand back from the details, and a steady theme appears. We live inside a flow of hidden signals and particles that rarely touch us, yet they sketch the structure of the cosmos and tie our small place to events across unimaginable distances. The chair, the wall, your breath, all are part of that larger context. The invisible does not sit behind a curtain. It shares the room. Cosmic rays are our first close contact with this wider world, arriving every second, nudged by dying stars, sculpted by black holes, and perhaps by relics of the universe's birth. They show that space is not empty, and that even the most silent places are full of motion. Within that steady rain, a few particles stand apart, the ultra-high energy kind. Some researchers suggest that the most energetic cosmic rays may come from beyond the part of the universe we can see. The observable universe has a boundary because light has had only so much time to travel since the Big Bang. What lies past that boundary could extend far beyond our horizon, perhaps without end. If so, a small fraction of these extreme particles might cross that edge and still reach us. They would act like messengers from regions no telescope can probe directly, slipping across the cosmic horizon and carrying clues about conditions that light itself cannot yet reveal. These particles do more than deliver news from far away. When a cosmic ray or one of its secondary particles passes through a living cell, it can sometimes nudge DNA. A strand may break, a base may flip, a repair enzyme may put it back together in a slightly different way. Most changes are harmless or quickly corrected, but some become true mutations. Over long spans of time, such random edits add to the pool of variation that natural selection sorts. Remove that background of particle-driven change, and the path of evolution would not be the same. The forms of life that appear, the branches that flourish or fade, the rare combinations that lead to new abilities, each is shaped in part by the slow rain of particles from space. The genetic story that leads to any person includes pages written by distant explosions. A star dies in another arm of the galaxy. A chain of collisions sends a high-energy particle toward Earth. Somewhere in an ancestor's cell, a letter in the code is altered. Many generations later, a trait persists because it helped a lineage endure. The connection runs deeper than the occasional mutation. Almost every atom in the body heavier than hydrogen and helium was minted in stars. Calcium in bone, iron in blood, carbon in every molecule of life. These elements were made by nuclear fusion in stellar cores, or during the brief, hot fusion that flares in a supernova's shock. When those stars ended, they threw their newly forged atoms into space. Over time, gravity gathered that material into clouds that cooled, clumped, and collapsed to form new stars and planets. The Sun and Earth were built from that recycled mix. In that sense, made of stardust is not a figure of speech but a plain description. Cosmic rays emphasize the point from another angle. Many are the newest matter we encounter, fresh fragments from recent stellar deaths, still carrying enormous energy, now crossing the galaxy to brush the older stardust that makes up living tissue. The rate at which these particles reach us is not fixed. Our solar system circles the center of the Milky Way roughly once every 213 million years. Along the way, it passes through regions with different amounts of gas, dust, magnetic fields, and star-forming activity. Where massive stars live and die, supernova remnants are common, and the local cosmic ray weather can be more intense. Geological records hint that the flux of particles at Earth has changed over deep time. In ice cores and ancient rocks, scientists look for isotopes that can be made by cosmic rays, such as beryllium-10 or carbon-14, to track past variations. The details are complicated because many processes can blur the signal, but the overall idea is straightforward. As the solar system moves through the galaxy, the particle environment changes, and the planet notices. One path for that influence may run through the atmosphere. When high-energy particles strike air molecules, they ionize them, knocking electrons free and leaving charged clusters behind. Those charges can help water vapor stick together, forming tiny seeds called condensation nuclei. With enough of these seeds and the right humidity and temperature, more droplets can grow into clouds. Low, bright clouds reflect sunlight back to space. If particle flux increases, clouds might slightly increase too, which could cool the surface. If flux decreases, there may be fewer seeds and less reflection, which could warm the surface. Some studies have explored whether grand ice age cycles line up with times when the solar system moves through the Milky Way's spiral arms, where there are more massive stars and supernovae. The idea is attractive and fits a simple physical story, yet it remains debated. Many climate drivers overlap: volcanic aerosols, greenhouse gases, solar variability, changes in Earth's orbit, and teasing out the separate roles is hard. Still, the possibility that the galaxy's structure leaves a fingerprint on climate is a reminder that Earth's system is open to space in more ways than sunlight alone. The same link to space shows up at smaller scales. Electronics on aircraft at high altitude can record sudden flips in memory bits when a stray particle passes through a chip. Astronauts sometimes report brief flashes of light with closed eyes, likely caused by particles crossing the retina. Airline routes, reactor monitoring, and satellite operations all include radiation budgets, because the particle background changes with altitude, latitude, and solar activity. The sun's wind, a stream of charged particles, shapes a bubble around the solar system called the heliosphere. During active solar periods, this wind can deflect some galactic cosmic rays, lowering the flux at Earth. During quiet periods, more make it in, That solar modulation sits on top of the larger, slower changes tied to the Milky Way's structure. The biggest energies return us to speculation at the edge of known physics. If an ultra-high energy particle arrives that seems too energetic to survive a long trip through the cosmic microwave background, we must decide whether it was born nearby or whether our picture of its journey needs revision. Some models imagine faint threads in space-time called cosmic strings, relics of early universe physics. If such a string kinks or snaps, it could release enormous energy in a small region, possibly producing a spray of particles at extreme energies. Other models look to tiny black holes formed not from stars but from early density spikes. Over billions of years, very small black holes should slowly radiate away their mass through quantum effects. In the last instant, the output would surge. Either idea would produce rare, powerful events without the kind of bright electromagnetic signatures that would have been easy to see already. Both ideas are unproven, but they show how cosmic rays can test theories that no laboratory can reach. Looking forward, it is natural to ask whether a civilization could use these particles on purpose. The highest energy cosmic rays carry the punch of macroscopic objects. Capturing such energy is not easy. The particles are rare. Their arrival directions are scattered by magnetic fields, and any detector would need a huge collecting area. Even so, a distributed array spread over a large landscape or anchored in space could in principle harvest some fraction, or at least use the showers they create as triggers for energy capture schemes. Communication is another thought. If a source could aim a controlled beam of ultra-high energy particles, the signal would be hard to block and would travel vast distances. Natural magnetic engines already exist near neutron stars and spinning black holes, where fields can act like rails that fling charged particles outward. If an advanced technology could shape those fields, it might imprint information on a beam. On our side, we would look for patterns in arrival times, directions, and energies that stand out from random backgrounds. So far, we see no confirmed patterns, but the search continues as instruments grow larger and more sensitive. For any future journeys beyond the solar system, cosmic rays move from curiosity to hazard. On Earth, the atmosphere and magnetic field reduce most of the dose. In interstellar space, there is no such shield. Thick walls help, but very dense materials can make a bad problem worse, because an incoming particle can smash into the shield and create a spray of secondary radiation inside the vessel. Passive shielding quickly becomes too heavy to push between stars. That pushes engineers to think about active ideas. One approach would generate magnetic or electric fields around a craft to deflect charged particles before they reach the hull, like a portable magnetosphere. Another path would make biology tougher. Drugs or gene edits that enhance DNA repair, add backup copies of key genes, or improve cleanup of damaged molecules. There are also staged flight concepts in which a small sacrificial craft flies ahead to absorb the first hits and clear a slightly safer corridor for the crewed ship following behind. Each approach faces hard limits, but together they frame the problem in practical terms rather than treating deep space as an impossible void. All of these threads return to a simple point. Earth sits inside a changing galactic environment. The particle background we measure today encodes more than local conditions. It contains a record of how often massive stars have died, where shockwaves still roam, and how active black holes have been in the recent past. In that way, cosmic rays act like a weather report at the scale of a galaxy, written in particles instead of pressure maps. By reading that report counting particles, mapping their energies and directions, and following how they vary with solar cycles, and over decades, we learn not only about violent sources far away, but also about the quiet, ongoing exchanges between space and life at home. Before we read the galaxy's weather any further, it helps to look at the rules that govern the smallest scales where those particles are born. Shift the viewpoint from fast particles to the small scale where rules change. At the quantum level, matter does not sit as fixed dots. It spreads out as a wave of chances, a pattern that tells us where a particle is likely to be found. An electron does not carry both a sharp position and a sharp momentum at the same time. This limit is the uncertainty principle. The more clearly one property is set, the fuzzier the other becomes. Before a measurement, the electron is described by a probability wave. The height of that wave at a place shows how likely it is to detect the electron there. This is not a gap in knowledge about a hidden, exact spot. The particle truly does not have a single location until an interaction forces a result. Physicists call this superposition, which means the system holds several possible outcomes at once. The famous double-slit experiment makes this clear. Fire electrons one by one at a barrier with two thin slits, then collect hits on a screen. Over time, the pattern on the screen shows bright and dark bands like ripples in water. The only way to get that pattern is if each electron behaves like a wave and in effect goes through both slits, with the two paths interfering. Place a detector to learn which slit the electron uses, and the bands disappear. The pattern changes to two simple piles, as if the electron chose a single slit. Taking path information destroys the wave-like superposition. Remove that information, and interference returns. The strange part is not that a device sits near the slits, it is the information. If the setup allows path data to be known, the interference fades. If the setup erases or never collects that data, the interference appears. Delayed choice versions push this further. The decision to keep or erase path information can be made after the electron has already passed the slits. Yet, the final pattern still follows the rule tied to the available information. It is tempting to say the electron knows about the measurement, but the safer lesson is that quantum outcomes depend on the whole experimental arrangement, including what information can, even in principle, to be extracted. Some people then ask whether human awareness is the special trigger. One family of ideas suggests that conscious observation collapses superpositions into single outcomes. In that picture, awareness holds a special place in physics. John Wheeler framed a bold version called the participatory universe. He imagined reality as a kind of feedback loop, where acts of observation help bring about definite histories, even hinting that late observations could set early conditions by way of quantum rules. These ideas are striking, but they are not required to explain experiments, and they raise hard questions about what counts as an observer and how awareness enters equations. A more standard view is decoherence. It says that any contact with the environment, air molecules, photons of light, a warm surface entangles the quantum system with many other degrees of freedom. That spread of correlation quickly destroys delicate phase relations that allow interference. The result looks like a collapse for all practical purposes. No special role for consciousness is needed. The world itself, always touching everything, performs a constant measurement. This explains why small, well-isolated systems show quantum behavior, while large, warm objects look classical. Still, a deep question remains about outcomes. Decoherence tells us why interference fades, but not why one result, and not another, is the one we actually see. That gap is known as the measurement problem. To ground the discussion, it helps to name the actors. A quantum state is a mathematical object that encodes all the chances for what we may observe. A wave function is one way to write that state. Superposition is the combination of several possible states at once. A measurement is any interaction that forces the system to yield a specific outcome. None of this says particles stop being real. It says reality at small scales is organized by probabilities and correlations rather than by fixed tracks. Entanglement makes those correlations stronger than any classical link. When two particles interact and then separate, their properties can remain tied. Measure one, and you instantly know what the other result must be if measured in a matching way, no matter how far apart they are. Einstein, Podolsky, and Rosen found this deeply unsettling. In 1935, they argued that such spooky action at a distance suggested quantum theory was incomplete. They proposed that hidden variables, not yet known, might fix outcomes in advance and remove any need for instant influence. If local hidden variables existed, the odd correlations would be an illusion made by averaging over missing details. Later work tested this hope. John Bell derived inequalities numerical limits that any local hidden variable theory must obey. Experiments with entangled photons, electrons, and even atoms have compared real data with those limits. Repeatedly, the results violate Bell's inequalities and match quantum predictions. The tests have tightened over decades, closing loopholes about detector efficiency and communication between devices. The pattern points to a conclusion that is simple to state and hard to accept in classical terms. Nature allows correlations that no local hidden variable model can reproduce. Entanglement does not send a signal faster than light, since no usable message rides on the correlation alone, but it does link outcomes in a way that stretches our everyday idea of separate objects. At the level of tools, entanglement is not just a puzzle, it is a resource. Quantum key distribution uses entangled pairs to reveal eavesdropping, because any attempt to intercept changes the correlations. Quantum computers aim to use superposition and entanglement to process many possibilities in parallel, offering speed-ups for certain tasks like factoring large numbers or simulating chemistry. Quantum sensors use interference to measure tiny changes in time, gravity, or magnetic fields with great precision. Each device works only when decoherence is kept low, which is why such machines are cold, shielded, and carefully isolated. The math behind all of this is compact but strict. Probabilities come from amplitudes, complex numbers whose squares give chances. Add amplitudes before squaring if paths are indistinguishable. Add probabilities if paths are distinguishable. That single rule explains the double-slit behavior and tells us when interference can appear. Phase, the angle part of an amplitude, carries information about how waves line up. Decoherence is the loss of fixed phase relationships to the environment. Measurement outcomes follow the Born rule, which ties the squared amplitude to the chance of a result. These are not just words in a textbook. They have been checked in countless settings, from electron microscopes to superconducting circuits. Even with that firm base, the border between the quantum and the classical remains blurry in practice. How large can a system be and still show interference? Physicists have demonstrated wave-like behavior with big molecules containing dozens or hundreds of atoms. Interference has been seen with cold clouds of thousands of atoms, acting like a single matter wave. The limit seems not to be size alone, but isolation. Keep a system quiet and shielded, and quantum effects can persist. Warm it up or connect it to a noisy environment, and classical behavior returns. A useful mental picture is to treat measurement as an interaction that spreads information. Before the interaction, many outcomes are possible. After it, the system and the measuring device are linked to a single outcome in a single record. Whether that link is created by consciousness, by a physical projection process, or by branching worlds depends on interpretation, but the lab result is the same. Set up for interference with no which path information, and waves appear. Set up to learn which path, and the waves are gone. The delayed choice ideas fit this picture too. If the setup is changed after the particle passes the slits but before detection, the final arrangement still decides whether path information exists. The observed pattern follows the rule tied to that final arrangement. No message is sent to the past. Rather, the quantum description spans the whole experiment at once, and the available information at detection time controls which terms in the description can interfere. Seen this way, the quantum realm is not chaos. It is ordered, but the order is statistical and relational. Properties are not fixed until interactions define them. Outcomes are not written in advance by local hidden numbers. Correlations can be stronger than any classical story allows, yet they do not break relativity's speed limit. The same rules that make superposition and entanglement puzzling also allow new kinds of measurement and new forms of technology. That picture is not just philosophy, it is measured. Decades of tests have shown that quantum entanglement is real and that no local hidden variable story can explain the data. John Bell wrote down clear mathematical limits that any such local theory must respect. Experiments then checked those limits and found repeated, clean violations that match quantum theory. Pairs of photons, electrons, and even atoms have been entangled and sent far apart across labs, under cities through fiber, and between ground stations and satellites hundreds of kilometers away, yet the correlations remain. The results at each site still look random by themselves, so no one can send a message faster than light. But once you compare the results, the pattern is stronger than any classical link could allow. At the quantum scale, distance does not act as a hard wall. What happens here is tied to what is possible there, in a way that does not fade with separation. This non-local tie suggests that reality cannot be broken down into independent, tiny parts that carry only local information. Some researchers have asked whether space-time itself might grow out of entanglement. In that view, the space we move through could be an emergent map drawn by networks of quantum links. Separate points in ordinary space might just be different faces of a deeper, connected structure. This idea is still under study and not a settled fact, yet it offers a simple thread. The stronger and richer the entanglement, the more room for space to exist, and changes in those links could shape geometry the way tension shapes a net. Quantum effects also show up in places that once seemed too warm and noisy for delicate states. Photosynthesis turns sunlight into chemical energy with striking efficiency. When a photon hits a pigment, like chlorophyll, it creates an excitation that must travel through a maze of proteins to a reaction center. Classical hopping from site to site would waste energy as heat. Lab studies on plant light harvesting complexes and on similar bacteria show signs of quantum coherence, where the excitation briefly explores many paths at once and then favors the best route. Coherence does not last long, often only femtoseconds to picoseconds, but that short window is enough to raise efficiency. The result is not magic. It is smart design by evolution. Keep the structure rigid enough, shielded enough, and tuned so that helpful coherence appears just long enough to guide energy flow before noise takes over. Bird navigation may use another quantum trick. Many migratory species sense Earth's magnetic field to find direction. A leading model points to a protein called cryptochrome in the retina. Blue light can create a pair of electrons on that molecule with linked spins, a radical pair. The quantum spin state of the pair responds to weak magnetic fields. Slight changes in field direction shift the relative populations of spin states, which then alter the chemical outcomes the bird can detect. For the sense to work, spin coherence must survive long enough to influence biochemistry, even at body temperature in a wet cell. Behavioral tests with altered light, radio frequency fields, and genetic changes support key parts of this picture, though details are still being tested. If correct, it would be a quiet example of life using quantum rules for a macro-scale task, a compass built from spin dynamics. The quantum view also changes what we mean by empty. A vacuum is not a true void. Quantum fields fill space, and their fluctuations allow pairs of virtual particles to flicker into and out of being for very short times. These are not ghost stories. They leave measurable marks. Put two uncharged metal plates very close together in a vacuum, and you find a tiny force pushing them together, the Casimir effect. The space between the plates restricts the kinds of field modes that can exist there, compared with the space outside, creating a pressure difference. Quantum corrections from such vacuum effects also fine-tune the magnetic moment of the electron, and precision measurements match the theory to many decimal places. In short, the vacuum has structure, and that structure can push on matter. That idea leads to a huge open problem when we look up at the cosmos. If all those vacuum fluctuations carry energy, every bit of space should have a built-in energy density. Quantum field theory lets us estimate it, and the raw answer is colossal, about 10, 120 times larger than the dark energy we infer from the gentle acceleration of cosmic expansion. Yet the universe is not flying apart at that impossible rate. Something in our counting is off, or some cancellation is at work that we do not yet understand. This mismatch, called the cosmological constant problem, is one of the widest gaps between theory and observation in modern physics. Ideas range from new symmetries that force a cancellation, to dynamical fields that relax the vacuum energy, to selection effects across many possible cosmic domains. None is confirmed. The plain fact remains: vacuum energy as we compute it is far too big, while the observed push-driving expansion is real, but tiny. To talk about these effects clearly, it helps to switch from particles to fields. In quantum field theory, each kind of particle is a ripple in a field that fills all of space. The electron field is everywhere. A single electron is a localized vibration of that field. Light is a ripple of the electromagnetic field. Quarks are ripples in quark fields. Forces show up as interactions between fields. Creation and annihilation of particles are just the field gaining or losing localized excitations. This view connects many facts at once. It explains why all electrons are identical. Each is the same type of field ripple. It explains vacuum effects. Even when no particles are present, the fields still have zero-point fluctuations. It explains why empty space can carry energy and momentum and can guide how matter behaves. Entanglement fits neatly into the field picture. Two excitations that have interacted can share a single joint state across distance because the underlying fields remain correlated. When a measurement locks in an outcome here, the field description there is updated in a way that keeps the shared structure consistent. No signal rides the link, so relativity's speed limit is safe, yet the correlations are stronger than any local classical account can allow. Bell tests confirm this by turning the idea into numbers and comparing with data. Over the years, experiments have closed loopholes about detector quality, sample choice, and timing. The trend is steady. Nature follows quantum rules. Non-local correlations and vacuum structure point to a delicate balance in how the world builds large-scale order from small-scale rules. On one hand, decoherence makes macroscopic objects look classical by spreading quantum information into the environment, so we do not see tables in superposition. On the other hand, carefully built systems can shelter coherence long enough to do work, from guiding energy in plants to stabilizing qubits on chips made of superconductors or trapped ions. Engineers fight noise with shielding, cooling, and error-correcting codes that detect and repair loss of quantum phase. Each gain in control lets us test the boundary between quantum and classical behavior with larger and more complex systems. Even the speed question has a clean answer once we track information. Entanglement links outcome statistics, but a single measurement result is random. To see the pattern, you must bring data together at normal speeds and compare. That is why entanglement cannot send a rescue message across light years. Still, the presence or absence of entanglement changes what joint measurements can reveal, which is why quantum key distribution can spot an eavesdropper. Tampering changes the joint statistics in a way that honest parties can detect. Quantum teleportation uses shared entanglement plus classical communication to move an unknown quantum state from one place to another without sending the physical carrier. None of this breaks relativity. It uses the rules as they are. As we refine tools, we also sharpen language. A measurement is any interaction that writes a stable record into the environment. A system is the part we consider and try to isolate. Collapse is the update from many possibilities to the one result recorded, whether you treat it as a physical process, an effective description from decoherence, or a branch in a larger wave function. In every lab, the same operational rule holds. Set conditions so that which path information is erased and interference appears. Set conditions so that path information exists and interference vanishes. The math that tracks amplitudes and phases gives the same answers no matter what story we tell around it. Pulling these threads together gives a plain picture. The small scale is not ruled by tiny billiard balls. It is ruled by fields, by probabilities, and by correlations that reach across distance, without carrying messages. Space may be less like a rigid stage, and more like a pattern woven by entanglement. Warm, living systems can, for brief windows, borrow quantum tricks to gain an edge. Empty space is an active medium whose energy we barely understand, and the constants that shape the large-scale universe may be telling us that our current theories are only parts of a deeper whole. Some versions of quantum theory hint that the past is not as fixed as it seems. At small scales, properties are not set until a measurement is made. In delayed choice and quantum eraser experiments, the final setup of the detector decides whether an interference pattern appears, even when that choice comes after the particle has passed the slits. The clean way to say this is that outcomes depend on the entire arrangement, including what information can, in principle, be known at detection. It looks like cause runs backward, but no signal is sent to the past. Instead, the quantum description stretches over the whole experiment at once, and the pattern we record reflects the information structure of that setup. Some interpretations go further and talk about retrocausality, future measurements selecting among past possibilities. Others keep cause and effect standard and say there is no need to change the past. We only update what we can consistently say about it when new data arrive. In all cases, the statistics match quantum rules. The experience in the lab is simple. Arrange things so which path information exists and interference vanishes. Arrange things so that information is erased and interference returns. Whether any of this means that history itself is unfinished until measured is a live question of interpretation, not a settled fact about time. Computing offers a practical window into these ideas. A classical bit is 0 or 1. A quantum bit, a qubit, can be in a superposition of 0 and 1 at the same time, and several qubits can be entangled so that the full system explores many combinations at once. Quantum algorithms use interference to amplify paths that lead to correct answers and cancel paths that do not. For specific problems, this gives powerful speedups. Shor's algorithm factors large numbers far faster than any known classical method. Grover's search provides a quadratic gain when looking through unstructured data. Quantum simulation is an even better match. Because molecules and materials are quantum systems, a controllable quantum device can mimic them directly, letting us predict chemical reactions, new drugs, better batteries, and exotic phases of matter. As devices scale, they may model quantum fields, the basic ingredients of modern physics, more faithfully than any supercomputer. That could let us test ideas about the early universe, where hot, dense fields dominated. Try out competing pictures of quantum gravity in toy settings, or track how space-time might emerge from patterns of entanglement. None of this requires new laws. It requires enough high-quality qubits with low error rates and long coherence times, plus error-correcting codes that spread information so that a few faulty parts do not ruin the computation. Underneath sits the measurement problem. What, exactly, counts as an observation that turns many possibilities into one recorded outcome? One line, associated with von Neumann and Wigner, places consciousness at the center, suggesting awareness collapses the state. This view tries to match the crispness of experience. We see one result, not a blur, but it raises hard questions. How conscious? Of what? And how does a mental event act on a physical state? Another line removes the special role of the mind. Decoherence says that any interaction with the environment, air, light, warmth, entangles a system with countless outside degrees of freedom. Phase relations then disperse into the environment and interference fades. Each branch of the joint system carries a definite record. For everyday objects, decoherence is so fast that we never notice quantum superpositions in the first place. No decisive experiment has proved that consciousness is or is not required. What we do have are mountains of cases where decoherence alone explains why lab devices yield stable outcomes without appealing to awareness. This is why most working physicists treat measurement as a physical interaction that writes a durable record, like a click in a detector or a mark on a screen, rather than a private mental event. Speculation about advanced technology must stay within these rules. Entanglement creates strong correlations over distance, but it does not carry usable messages faster than light. Any claim of instant communication by entanglement alone breaks the statistics we measure. A quantum network could still be remarkable. It could share keys for ultra-secure communication, teleport quantum states with help from a normal light-speed channel, and link distant sensors so that joint measurements beat classical limits. Keeping large systems coherent long enough for massive quantum computation is also a severe challenge. Yet in principle, error-corrected qubits could support tasks beyond any classical computer, simulating complex proteins, designing new catalysts, or solving optimization problems with new quantum heuristics. Quantum tunneling adds another twist. A particle has a chance to appear on the other side of a barrier it classically cannot cross. This is a real, measured effect that helps set nuclear reaction rates in stars and enables devices like tunnel diodes and scanning tunneling microscopes. Moving macroscopic objects or people by tunneling is not supported by current physics. The probabilities drop to effectively zero. Ideas about tunneling through space-time itself belong to speculative theories of wormholes and quantum gravity. They are useful as thought experiments, but they are not engineering plans. The information view of physics brings these pieces together. In quantum information theory, what matters most are the relations among states, amplitudes, phases, and correlations. Entanglement is a kind of information resource. Measurement is an information updating event that ties a system to a record. Error correction protects fragile quantum information by spreading it over many physical carriers. From this angle, matter and energy look like ways information is stored and moved by quantum fields. That is not just a metaphor. The electron's identity is the state it occupies in the electron field. A photon is a state in the electromagnetic field. Forces are rules for how information in one field affects information in another. Push the idea further and you reach the universe computes. Each interaction is a small update. The whole cosmos is a vast, parallel process that steps forward according to simple rules we write as equations of motion. This is a picture, not a proof. It helps frame questions. Which rules generate space-time? Which rules fix the size of the dark energy push? Which error-correcting structures could make geometry stable against quantum noise? Some proposals even say our world could be a simulation run on a deeper quantum substrate. That moves the puzzle up a level rather than solving it. What runs that substrate, and what counts as real in such a stack? For now, the useful lesson is modest. Tracking information, what can be known, shared, or erased, predicts outcomes in the lab and guides designs for new devices. Even without final answers, quantum theory already shapes daily life. Lasers, GPS timing, MRI scanners, LEDs, and the chips in phones all rely on quantum rules. Atomic clocks use interference in well-isolated atoms to keep time so steady that GPS can locate a receiver to meters by timing radio signals. Superconducting circuits, cooled near absolute zero, switch without resistance and form qubits for many current quantum processors. Nitrogen vacancy centers in diamond hold quantum states at room temperature long enough to act as sensors of magnetic fields inside living cells. These practical wins come from learning to isolate, manipulate, and read out fragile states before decoherence washes them away. Several plain statements survive the maze of interpretations. Quantum experiments never show signals outrunning light. They do show correlations that no local hidden variable model can match. Measurements depend on available information, not on a detector's mere presence. Decoherence explains why large objects behave classically, while leaving an open question about why a single outcome is observed rather than a spread. Superposition and entanglement are not side notes. They are central features that let devices outperform classical limits when protected and used well. Seen in a calm light, the quantum world is neither mystical fog nor a tidy clockwork. It is a rule-bound domain where probabilities, phases, and correlations carry the story, where fields, not little pellets, are the basic actors, and where information is the thread that ties small systems to big ones. On the largest scales, most of what shapes the universe does not shine. Dark matter and dark energy make up about 95% of all mass energy, while the stars and gas we see account for less than 5%. We know this not because we can catch the dark parts with a telescope, but because of how gravity pulls on what we can see and how space itself expands. The clue for dark matter first appeared in how galaxies rotate. In a simple picture, material far from a galaxy's center should move more slowly, the way distant planets orbit the sun at lower speeds than the inner ones. In the 1,970 seconds, Vera Rubin and her colleagues measured rotation curves, orbital speed versus distance for many spirals and found something different. Speeds stayed high and nearly flat even far beyond the visible edge. If the mass were only the stars and gas we see, the outer parts should fly off. They do not. The clean fix is extra mass in a large, unseen halo holding everything together. That halo idea fits many lines of evidence. In galaxy clusters, galaxies move faster than visible mass can support. Hot X-ray gas in clusters needs extra gravity to keep it bound. On even larger scales, maps of how far away galaxies appear stretched or magnified, an effect called gravitational lensing, show extra mass bending light. The pattern of tiny temperature spots in the cosmic microwave background, the afterglow of the Big Bang, also points to a mix of components that includes a large share of non-glowing matter. All of these measurements, done with very different tools, point to the same answer. There is more gravitating stuff than meets the eye. Dark matter also solves a timing problem. The early universe was almost uniform, with small ripples in density, about 1 part in 100,000. Ordinary matter felt radiation strongly, so it could not clump until after atoms formed, about 380,000 years after the Big Bang. That delay would leave too little time to build the galaxies and clusters we see today. Dark matter does not interact with light, so it could start gathering while the universe was still a hot plasma. Its early clumps formed gravity wells. Later, ordinary gas fell into those wells, cooled, and made stars. Computer simulations that include a dark component produce a web of filaments and nodes that matches large-scale galaxy surveys. Without the dark scaffolding, the model universe stays too smooth for too long. If we could see the dark network directly, space would look like a vast three-dimensional web. Dense strands span hundreds of millions of light-years. They meet at nodes where clusters of galaxies live. Between them are wide voids, with very little matter. Galaxies do not draw this structure. They trace it. They turn up where the dark matter density is higher, because that is where gas can collect and form stars. The overall architecture, the where and the when, is set by dark matter, while ordinary matter fills in the visible details. What is dark matter made of? The leading idea for years was a new kind of particle that barely interacts, neither charged nor bright, but massive enough to pull with gravity and perhaps to feel the weak nuclear force. These candidates are called WIMPs, weakly interacting massive particles. In the hot early universe, WIMPs would have collided often. As space expanded and cooled, they would freeze out, leaving a leftover amount that lines up neatly with what we infer. Supersymmetry, a proposed extension of the standard model of particle physics, offers a natural WIMP candidate called the neutralino. Searches for WIMPs are direct and careful, deep underground, where rock blocks most cosmic rays. Teams build detectors from ultra-pure liquids or crystals cooled close to absolute zero. They wait for the faintest nudge, a tiny kick to an atomic nucleus that could come from a passing dark particle. The instruments watch for rare flashes of light, heat, or charge that mark such a collision. With each year, sensitivity improves. So far, results are null, and those nulls matter. They rule out large swaths of interaction strengths and masses. Theory adjusts. Experimentalists move to bigger detectors, cleaner materials, and new methods. But the simple WIMP picture is no longer the only favored path. Another candidate is the axion, a very light particle first proposed to solve a puzzle in the strong nuclear force called the strong CP problem. Axions would be produced in huge numbers in the early universe. Even though each carries little mass, the total could be enough. Axion searches look for a tiny conversion of axions into photons in strong magnetic fields, often using microwave cavities or resonators tuned to a narrow range of possible masses. The challenge is that the allowed mass range spans many orders of magnitude, so experiments must scan slowly, like tuning a radio through static to find a whisper of a station. Some researchers have returned to an old idea: primordial black holes. In the first fractions of a second, small regions could have been dense enough to collapse directly into black holes without stars. If many formed, they could act as dark matter. Gravitational wave observatories have found black hole mergers with masses that surprise some models of stellar evolution, which keeps interest in primordial populations alive. But most tests, microlensing surveys, the pattern of the microwave background, and limits on early universe heating press hard on how much of the dark matter these black holes could supply. The balance of evidence still favors a particle explanation, though the door is not fully closed. A different route tries to change gravity instead of adding matter. Under the name MOND, or Modified Newtonian Dynamics, proposals adjust how gravity behaves at very low accelerations, like those at the edges of galaxies, to flatten rotation curves without halos. Relativistic versions, such as TVs, aim to respect Einstein's theory, where it has been tested while recovering MOND-like behavior on galactic scales. These models can fit some galaxy data, but they struggle with cluster observations and with systems like the Bullet cluster. In that famous collision of two galaxy clusters, the hot gas, most of the visible mass slowed down and lagged in the middle, while most of the gravitating mass, mapped by gravitational lensing, sailed ahead with the galaxies. That is what you expect if dark matter particles passed through each other with little friction. It is much harder to reproduce with only modified gravity and no extra mass. Lensing maps of other colliding clusters show similar offsets. Dark matter alone does not complete the picture. The expansion of the universe itself is speeding up. In the late 1990 seconds, two teams used Type Ia supernovae standardizable candles to measure how fast distant galaxies were receding long ago. Instead of slowing under gravity, the expansion had begun to accelerate a few billion years after the Big Bang. The simplest way to include this effect in Einstein's equations is a cosmological constant, often written as Lel lambda, which acts like a uniform energy density of empty space. We call the driver of this acceleration dark energy. Combine supernova results with the microwave background and with how galaxies cluster on large scales, features called baryon acoustic oscillations, and the case for dark energy is strong. Today's best fits split the cosmic energy budget roughly as about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. What is dark energy? The most conservative answer is that it is the vacuum energy of quantum fields, a constant energy per unit volume of space. That matches data well if its pressure is negative and equal in size to its energy density, a relation written as an equation of state parameter, W equals 1. Measurements so far place W close to 1 within errors. The puzzle is theoretical. Naive quantum field calculations predict a vacuum energy far, far larger than observed. Why is the real value so small? Some models introduce a slowly rolling field, often called quintessence, that changes over time and space, mimicking a dark energy like push, with W near, but not exactly 1. Others try new couplings or modified gravity on the larger scales. Observations keep narrowing the space of options by tracking how the expansion rate and the growth of structure change with time. Dark energy leaves marks besides dimmer supernovae. It affects the pattern of the cosmic microwave background by changing distances to the last scattering surface. It alters how fast small ripples grow into big structures, which we can read from galaxy surveys and weak lensing maps of how matter distorts the shapes of background galaxies. It changes the scale seen in the baryon acoustic oscillation feature the relic sound waves imprinted in the distribution of galaxies. By cross-checking all these probes, cosmology tests whether a simple L fits or whether new physics is needed. Current data remain consistent with LL, though tensions exist, such as differing measurements of today's expansion rate, the Hubble constant, from early universe and late universe methods. Those tensions may come from subtle systematics, or they may hint at missing pieces in our model. Even without a full identity card for either dark component, we can work with their effects. In simulations, dark matter sets up wells, gas falls in, stars form, supernovae and black holes heat and stir the gas. Feedback regulates growth. The result is a universe that looks like ours when you render it into mock images and compare to sky surveys. In the lab and in underground halls, detectors push toward the faint signals expected from rare dark matter interactions. In radiolabs and microwave rooms, axion searches sweep through frequencies. At accelerators, teams look for new particles that could play the dark role, or for tiny deviations from the standard model that point to a richer sector. On the sky, lensing surveys measure how mass, dark and visible together, bends light across wide fields. Galaxy redshift surveys map three-dimensional structure over billions of light-years to watch growth over time. Supernova teams extend their reach to earlier eras. Cosmic microwave background missions sharpen maps of temperature and polarization to extract more detail about the early universe. Each new dataset tightens the web of facts that any theory must match. A few simple summaries help anchor the ideas. Dark matter acts like extra gravity without light. It clusters, it builds halos, it shapes where galaxies form, and it leaves lensing patterns offset from hot gas in collisions. Dark energy acts like a gentle, persistent push. It speeds up the expansion, stretches the scale of distances, and slows the growth of new structure by pulling everything apart more quickly. The numbers we quote, about 27% and 68%, come from fits that use many independent probes at once. Change one probe, and the others still point to a large, dark sector. Open questions guide the next steps. If dark matter is a particle, what mass and what interactions does it have? If it is many particles, what simple pattern ties them together? If it is not a particle, what compact alternative can reproduce cluster lensing, the microwave background, and the cosmic web at the same time? 4. Dark energy. Is W exactly 1 or slightly different? And does it vary with time? Are the Hubble constant tensions telling us about measurement challenges or about new physics in the first or later billion years? Answers will likely come not from a single breakthrough, but from steady cross-checks, deeper surveys, cleaner detectors, and better theory that connects the small to the large. All of this sits next to daily life more than it seems. GPS and satellite orbits require general relativity for accuracy, the same framework used to model expansion. The elements in our bodies formed in stars that grew inside dark matter halos. The pattern of galaxies on the sky helps set the targets for telescopes and missions we build. The universe at scale is not a blank backdrop. It is an active stage whose unseen parts steer the story of how structure forms, how light travels, and how time flows from the hot beginning to the cold future. Some researchers consider a darker mirror of the cosmos, a sector that overlaps our space, yet interacts with us only through gravity. In that picture, dark matter would not be a loose fog alone. It could carry its own forces, dark electromagnetism, with dark photons, and its own bound states, like dark atoms and dark molecules. If such forces exist, dark matter could cool by radiating dark light, condense, and build layered structures. A dark halo might hide clumps within clumps, perhaps even dark disks, dark stellar nurseries, and systems that look gravitationally like stars with planets. None of this would shine in our telescopes. We would notice only by how the mass tugs on ordinary matter, by how starlight bends as it passes, or by how orbits curve a little more than expected. A full dark matter galaxy could occupy the same volume as the Milky Way, with orbits, mergers, and even a massive dark object at its center, yet remain invisible except for its pull. If the dark sector's self-interactions are weak but non-zero, new paths open. Collisions among dark particles could let some lose energy and sink toward the centers of halos. Over billions of years, the densest places galaxy cores, star clusters, even the interiors of stars and planets might gather small reservoirs of dark matter. In stars, a slow trickle could change the balance of heating and cooling by adding an extra energy term when trapped dark particles annihilate or scatter. Such effects would be subtle, but they could shift lifetimes or brightness by small amounts and might explain oddities in some stellar populations, if confirmed. On planets, including Earth, accumulated dark matter would be far too diffuse to notice directly, yet in principle, it could leave faint fingerprints in heat flow or neutrino signals. These ideas remain speculative. They point experiments to the right questions. How strongly do dark particles scatter? How often do they self-annihilate? And where would those processes leave an observable mark? The tools we use to probe such hidden sectors are built from quantum rules. A quantum bit, or qubit, can hold a superposition of 0 and 1 at once. With many qubits entangled together, a device can choreograph interference among an enormous number of paths in parallel. Quantum algorithms steer that interference so that wrong answers cancel and promising answers add. For certain problems factoring with Shor's algorithm, search with Grover's, or simulating quantum materials, the speed-ups can be dramatic compared with any known classical method. The most natural arena is simulation. Chemistry, magnets, superconductors, and nuclear reactions are quantum systems. Using quantum hardware to mimic them is a direct match. As coherence times improve and error-correcting codes spread information across many physical qubits, machines may tackle models that track quantum fields themselves, the basic language of particle physics and the early universe. Such simulations could test how small ripples in a hot field grew into structures, or how different rules for gravity at tiny scales affect the birth of space-time. They will not change the laws of nature, but they can preview which ideas survive contact with detailed dynamics. Alongside computing sits the old puzzle of measurement. What turns a spread of possibilities into one recorded result? One family of views puts conscious awareness at the pivot. An idea linked to von Neumann and Wigner, a mental act, collapses the state. It tries to account for the crisp feel of experience, yet it lacks a clear mechanism and blurs the line between physics and mind. The alternative is decoherence. Any interaction with the environment entangles the system with countless outside degrees of freedom, washing out the phase relations that allow interference. A detector click is enough. A warm surface is enough. In practice, this view explains why we get stable outcomes without invoking awareness, though it leaves an open question about why a single outcome is realized rather than a spread of branches in our experience. Speculations about advanced civilizations often lean on these same principles. Entanglement creates strong correlations across distance, but it cannot carry usable messages faster than light. A real quantum network would still need a classical channel to share results. Even so, such a network could be powerful. It could distribute secret keys that reveal eavesdropping, teleport quantum states with high fidelity, and link far-flung sensors into one instrument that beats classical limits. If a culture learned to keep large, warm systems coherent far beyond our present reach, it could run computations and simulations on scales that dwarf ours, solve hard optimization problems, and design materials or medicines by modeling them directly. Quantum tunneling, a real effect where a particle crosses a barrier it could not pass classically, already powers nuclear fusion in stars and enables scanning tunneling microscopes. Extending tunneling to macroscopic transport, or jumps, across space-time remains fiction with current physics. The probabilities fall to effectively zero for large objects, and nothing in the data supports shortcuts through space. Another thread ties to information itself. In quantum information theory, what defines a system is not little pellets of substance, but the state of a field, and the relations, amplitudes, phases, and correlations within and between systems. Measurement is an information event. A record is created. Chances become frequencies in that record. Error correction keeps fragile quantum information alive by spreading it across many qubits so local noise can be detected and reversed. From this angle, matter and forces look like patterns in quantum fields that store and process information. Push the picture further, and the universe looks like a computation unfolding. Each interaction updates the global state. The laws of physics play the role of a program. The tick of time feels like the progress of these updates. This is a model, not a proof. It organizes questions. Which information patterns build space? Which protect geometry from quantum noise? And which set the small value of the dark energy push? Versions that say our world is a simulation simply move the question up a layer and ask what runs the simulator. The useful part is nearer to home. Track what information is available or erased in an experiment, and you can predict what patterns will appear. Quantum mechanics, then, is not confined to the small. It shapes how we think about space, time, causation, and even awareness. It could turn out to be an effective face of a deeper theory, quantum gravity, that also includes the geometry of space-time and explains why quantum rules hold. Or it could be fundamental, with probability, uncertainty, and non-local correlations as basic features of existence that we learn to live with rather than remove. Either way, the same framework that gives us lasers, MRI, and atomic clocks also frames our search for the dark sector that dominates the cosmos. On that larger stage, dark matter and dark energy set the budget. Everything that glows stars, nebulae, the bright arcs of galaxies, adds up to less than 5%. The rest, we infer from its pull and from the way distances change as the universe expands. Dark matter first stood out in galaxy rotation. If mass followed light, outer stars in a spiral galaxy should orbit more slowly as distance grows, like the outer planets around the Sunday. Careful measurements in the 1,970 seconds by Vera Rubin and collaborators showed something else. Rotation speeds stay high and roughly flat far past the visible edge. Many other signs line up with that result. In clusters, galaxies move faster than visible mass combined. Hot gas shining in X-rays needs extra gravity to hold it in place. Weak gravitational lensing tiny, coherent distortions in the shapes of background galaxies maps extra mass not accounted for by starlight. The cosmic microwave background encodes the early universe's contents and points to a significant dark component. Simulations that include dark matter produce a cosmic web, filaments spanning hundreds of millions of light years, meeting at massive nodes, with wide, quiet voids between. Galaxies form along the filaments where dark matter density is highest, because that is where gas falls in and can cool. Dark matter makes up about a quarter of the cosmic energy budget. Its nature is still unknown, but the leading pictures are being tested from many sides. Underground detectors listen for rare taps from a passing particle. Microwave cavities scan for axions converting to faint photons in strong magnetic fields. Telescopes map lensing to watch how mass clumps and grows. Accelerators search for new particles that could play the dark role or point to new symmetries. Some theorists keep exploring modified gravity ideas that change how attraction works on very low accelerations. Those systems like the bullet cluster, where most of the gravitating mass kept going while the visible, colliding gas lagged, are straightforward to explain with particle dark matter and hard to match with gravity tweaks alone. Alongside dark matter sits dark energy, the label for the slow, steady acceleration of the expansion. Type Ia supernova data, the scale of baryon acoustic oscillations in galaxy surveys, and the detailed patterns in the microwave background all agree. A smooth component with negative pressure dominates today. The simple model, a cosmological constant L with equation of state parameter W equals -1 fits current data well, though tensions remain over the exact value of the current expansion rate. Field-based alternatives, like quintessence, remain possible. So do more radical changes to gravity on horizon scales. New surveys, deep imaging for weak lensing, larger supernova samples, and better maps of galaxy clustering are aimed at pinning down whether W is exactly 1 and whether it changes over time. The more detailed the maps, the more room there is for a rich dark sector. If dark matter has self-interactions, even weak ones, cluster collisions might show slight offsets or cores where density flattens. If some fraction is in ultralight particles, structures on the smallest scales could be blurred. If axions exist, they might produce narrow spectral lines in specialized detectors. If primordial black holes contribute, rare microlensing events or specific signatures in the microwave background would mark their presence. Each clue would change how we read the gravitational scaffolding around us. Meanwhile, hypotheses about dark stars, dark planets, and dark chemistry remain in the realm of models. They are useful because they teach us what to look for: ripples in stellar motions, odd lensing events, slight mismatches between mass maps and light maps that repeat in a way only a structured dark disk could explain. If dark matter can cool by emitting dark photons, it could form disks aligned or misaligned with visible ones. If not, it will remain puffed up and halo-like. The Milky Way's halo might contain cold streams of dark matter from past mergers, crossing our neighborhood and leaving periodic signals in detectors on Earth. Annual modulation searches already look for tiny seasonal changes as our planet moves through the halo and the flux of particles shifts by a small amount. In that layered picture, ordinary matter is the tracer. It lights up the densest parts, marks shock fronts where gas falls in, and records feedback from supernovae and black holes. Dark matter provides most of the binding. Dark energy sets the long-term stretch of space. The two together decide where structures form, how fast they grow, and how the cosmic web changes with time. Our job is to read the traces with the best tools we can build: quantum devices that sense faint signals, telescopes that see across bands from radio to gamma rays, and careful statistics that let us combine many kinds of evidence into one consistent picture. Computer models that include gravity, radiation, and gas dynamics show a consistent result. Without a non-luminous mass component, galaxies would not have formed in time. The early universe was astonishingly smooth. Tiny ripples only about 1 part in 100,000 are visible today, as faint, hot and cold spots in the cosmic microwave background. Ordinary matter, made of protons, neutrons, and electrons, was tightly linked to light in that era. Photons scattered off free electrons and kept the gas hot and pressure supported. Under those conditions, gravity alone could not pull ordinary matter into dense knots quickly. Only after the universe cooled enough for electrons to join nuclei and make neutral atoms, about 380,000 years after the Big Bang, could the gas start to fall inward. By then, precious time had passed. If there were no dark matter, the tiny ripples would still be growing too slowly today, and the sky would show a fog of diffuse gas rather than the sharp structure we observe. Dark matter solves the timing. Because it does not interact with light, it began to clump much earlier, while the cosmic soup was still a plasma. Small overdensities grew into halos, gravitational wells that deepened over time. When atoms finally formed and the fog of free electrons cleared, ordinary gas could stream into those wells. As gas piled up, it cooled by radiating away heat, settled, and formed the first stars. Those stars lit the universe and seeded it with heavy elements. Later, halos merged with halos. Small systems combined into larger ones, and the first galaxies took shape. Simulations that include dark matter and simple recipes for how gas cools and forms stars naturally build a universe that looks like ours in broad strokes. The large-scale map that emerges is a web. If we could see dark matter directly, space would resemble a three-dimensional net. Long filaments spanning hundreds of millions of light-years, intersecting at crowded nodes where galaxy clusters sit, and enclosing wide voids that are nearly empty. Visible galaxies trace those filaments, because that is where gas has been gathered. Spiral galaxies decorate the strands. Massive ellipticals often live in the nodes. Dwarf galaxies wander the outskirts or hide within bigger halos. The web's overall geometry comes from dark matter, while ordinary matter paints the structure with light. Even with this clear role, the nature of dark matter remains open. It accounts for roughly 27% of the total energy budget of the universe, but it does not shine, absorb, or scatter light in any way we have measured. One long-standing idea is that dark matter is made of new particles that feel gravity and possibly the weak nuclear force, but not electromagnetism. These hypothetical particles, called WIMPs, weakly interacting massive particles, would have been abundant in the hot early universe. As space expanded and cooled, their production would stop, and a leftover population would survive. Simple versions of this thermal freeze-out story neatly produce the right abundance. Supersymmetry, an extension of the standard model of particle physics, predicts families of partner particles for known ones. In many supersymmetric models, the lightest neutral partner, the neutralino, is stable and fits WIMP expectations. That motivated a three-pronged search. Look for WIMPs produced in high-energy collisions at accelerators. Look for signs of WIMP annihilation in space, such as excess gamma rays or antimatter. And look for WIMPs scattering off atomic nuclei in underground detectors. Direct detection experiments are built like quiet, shielded ears, deep beneath mountains, or in old mines where rock blocks most cosmic rays. Large tanks of ultra-pure liquid xenon, argon, or supercooled crystals wait in the dark. If a dark matter particle bumps a nucleus, the recoil can produce a tiny flash of light, a small amount of ionization, or a whisper of heat. Arrays of sensitive sensors watch for those signals while rejecting backgrounds. Over the past decade, these detectors have grown and become exquisitely clean. So far, no undisputed WIMP signal has appeared. That absence is not empty. It rules out broad ranges of possible masses and interaction strengths, and has pushed theorists to refine models or consider new ideas. One such idea is the axion, a very light particle proposed to solve a puzzle in the strong nuclear force called the strong CP problem. If axions exist, the early universe would have produced vast numbers of them. They would hardly interact, but together they could provide the right amount of dark mass. Axion searches use different tools than WIMP hunts. A leading method places a strong magnetic field across a microwave cavity or a high-Q resonator. In such a field, axions could convert into photons at a frequency set by the axion mass. By slowly tuning the cavity and listening for an extra whisper of power, experiments scan through possible masses. The challenge is the enormous range of possibilities, so the search proceeds like turning a dial across many empty channels to find a single faint station. Another path revisits black holes born in the first instance after the Big Bang. In those conditions, density peaks could have collapsed directly into black holes without ever being stars. If enough formed, they could act as dark matter. Observations from gravitational wave detectors have found black hole mergers with masses that surprised some stellar models, keeping interest in primordial black holes alive, but limits from microlensing surveys, the smoothness of the cosmic microwave background, and the dynamics of dwarf galaxies press hard on how large a contribution these objects can make. The balance of data continues to favor a particle explanation, though the window is not completely closed. A very different approach tries to adjust gravity on large, low-acceleration scales instead of adding new matter. Modified Newtonian dynamics, or MOND, changes the force law, where accelerations are tiny, flattening galaxy rotation curves by design. Relativistic versions, such as TVs, aim to keep agreement with general relativity in the solar system and in strong gravity tests, while shifting behavior in galaxies. These theories can fit some rotation curves well, but they face challenges with galaxy clusters, the cosmic microwave background, and colliding cluster systems. The bullet cluster is the textbook case. Two clusters passed through each other. Their hot, X-ray bright gas interacted and slowed, while the bulk of the gravitational mass, mapped by weak lensing of background galaxies, moved ahead with the collisionless galaxies. That spatial offset is exactly what you expect if most of the mass is in particles that pass through with little friction. It is far harder to reproduce by tweaking gravity alone without unseen mass. Speculative, dark sector models add richness rather than remove it. In these, dark matter could have its own forces, dark electromagnetism, dark photons, and form dark atoms and molecules. If it can radiate energy as dark light, it can cool and condense, perhaps forming disks, clumps, or even dark analogs of stars and planets. Such structures would not shine in ordinary light and would be nearly invisible except for gravity. A dark disk aligned with or tilted relative to the Milky Way's visible disk could leave subtle signatures in stellar motions or microlensing patterns. Streams of dark matter from long ago mergers might cross the solar neighborhood, altering detection rates on Earth by a small yearly rhythm as our planet moves around the sunday. Searches for seasonal modulation already look for such patterns in underground data. If dark particles have weak self-interactions, they could slowly sink toward the centers of halos or be captured by stars and planets. Inside stars, captured dark matter might annihilate or scatter and add a small heat source that could slightly change lifetimes, sizes, or oscillation patterns of certain stars, effects that might be probed by asteroseismology, which studies starquakes through brightness variations. On planets, including Earth, accumulated dark matter would be extremely diffuse and hard to detect, but in principle might show up as tiny extra heat or as rare neutrinos from annihilations deep inside. These possibilities sit at the edge of current sensitivity and guide the design of future detectors. Upcoming observatories promise sharper mass maps and better tests. Gravitational wave detectors can, in the primordial black hole scenario, measure merger rates and mass distributions that trace early universe conditions. The Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory, with its legacy survey of space and time, will map weak gravitational lensing across large areas and depth, tracing how matter dark and visible clumps over time. They will also measure the expansion history through supernovae and baryon acoustic oscillations with high precision. With those tools, astronomers can check whether the equation of state of dark energy behaves like a pure cosmological constant or varies slightly with time, and whether growth of structure proceeds exactly as expected under general relativity or shows small departures that hint at new physics. Within this framework sits the visible universe of galaxies. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter, often with a supermassive black hole at the center. Spirals show thin disks with arms traced by young blue stars and glowing gas. Bars' elongated central features can funnel gas inward and feed star formation or the central black hole. Ellipticals are rounder or football-shaped, dominated by older, redder stars with little cold gas. Dwarf galaxies can be irregular and faint, shaped strongly by their environment and by bursts of star formation and feedback. Collisions and mergers are common across cosmic time. When galaxies interact, tidal forces pull out long tails, drive gas to the center, and can ignite starbursts. Over billions of years, repeated mergers can turn a spiral into a larger, smoother elliptical and grow the black hole at the core. The growth of galaxies is a balance between inflow, star formation, and feedback. Gas flows in along filaments, cools, and forms stars. Massive stars and supernovae heat and stir the gas. Active galactic nuclei, powered by matter falling into central black holes, can launch jets and winds that push gas back out. This feedback keeps galaxies from turning all their gas into stars at once and helps set the observed relation between a galaxy's mass and its star formation rate. The dark halo sets the stage by defining the potential well. The size and spin of the halo influence the size of the disk. The merger history shapes morphology. Star formation and feedback paint the observable features. Across all types, the invisible mass remains the backbone. Gravitational lensing shows halos extending far beyond visible edges. Satellite galaxies orbit within those halos. Stellar streams from shredded dwarfs trace the underlying potential like ink in water. Astronomers use many bands of light to read this history. Radio maps reveal cold hydrogen gas, the raw fuel for future stars. Infrared sees dust-shrouded star formation and older stellar populations. Optical spectra show the motions of stars and gas and the chemical fingerprints left by past generations of stars. X-ray images highlight hot gas in clusters and the energetic neighborhoods around black holes. Each band adds a layer to the same story. Gravity builds structure on the dark scaffold. Gas cools and forms stars. Feedback moderates growth. And the largest shapes we see are the surface features of a much deeper, unseen mass distribution. In clusters, the largest bound structures, dark matter's role is especially clear. The hot intracluster gas, reaching tens of millions of degrees, shines in X-rays and accounts for more visible mass than the stars do. Yet even adding gas and stars falls short of what is needed to bind the cluster. Weak lensing maps show the full mass distribution, and it aligns with the galaxies rather than with the slowed, collisional gas in merging systems. This separation in space between the main gravitating mass and the brightest baryonic component is a straightforward signature of collisionless dark matter. On smaller scales, the exact behavior of dark matter can leave fingerprints. If it is perfectly cold and collisionless, simulations predict many tiny subhalos within larger halos, some of which can host dwarf galaxies and some of which might remain dark. The number and internal structure of dwarf galaxies around the Milky Way test that prediction. If dark matter has even slight self-interactions, the densest cores of halos might be a bit fluffier rather than steeply peaked. Astronomers compare rotation curves of dwarf galaxies and lensing in small systems to these expectations to constrain interactions. The search is broad by design. Underground detectors listen for rare scatters. Cavities and resonators search for axion conversions. Telescopes map lensing and galaxy clustering to track mass and growth. Gravitational wave instruments catch mergers that could hint at primordial populations. Particle colliders look for hints of new fields or symmetries that could anchor the dark sector. Each constraint narrows the space of possibilities, and each improvement in sensitivity or sky coverage makes the remaining picture sharper. Across this landscape, the main outline stays steady. The universe began nearly smooth, with tiny ripples. A non-luminous mass component clumped early and helped structure grow fast enough. Ordinary matter fell into those wells, cooled, and lit up as stars and galaxies. The web of filaments, nodes, and voids is the natural result of gravity acting on matter over time. The details, whether the dark particle is heavy or light, whether it has self-interactions, whether a small fraction hides in primordial black holes, are the open parts. The visible forms we admire, spiral arms, star-forming rings, giant ellipticals, thin stellar streams, are the bright traces that let us infer the invisible shape beneath. At the centers of most large galaxies sits a supermassive black hole, packing millions or billions of suns into a region smaller than our solar system. In the Milky Way, the central object is called Sagittarius A*. Its mass is about 4 million suns. Astronomers know this not by seeing the black hole directly, but by watching nearby stars move. Using infrared telescopes to look through dust, they have tracked individual stars looping around the center along clean ellipses. One star, S2, has been followed for over 25 years. It completes an orbit every 16 years, swings in to about 20 billion kilometers at closest approach, and whips around at more than 5,000 kilometers per second, roughly 2% of light speed. The math from these orbits fixes the mass and size of the unseen object. Nothing except a black hole can be that compact and that heavy at the same time. Black holes and their galaxies seem to grow together. Observations show a tight tie between the mass of the central black hole and the mass of the galaxy's bulge, the bright, rounded core made mostly of older stars. A common rule of thumb is that the black hole holds about 0.1% of the bulge mass. This pattern holds across many kinds of galaxies and over a wide range of sizes. It hints at feedback. Gas that falls inward feeds both star birth in the bulge and the black hole. Energy from the black hole then pushes back on the gas, heating it or launching it outward so that star formation slows. In some eras, the black hole is quiet. In others, it blazes. When matter piles into the center, it forms a hot, bright disk and can drive jets of particles at near light speed. These active galactic nuclei can outshine all the stars of their host, carve out cavities in hot gas, and change how and where new stars form far from the center. Galaxies do not live alone. They tug on each other, pass close, and sometimes merge, even in a direct hit. Stars almost never collide because the gaps between them are vast. The main effects are gravity's long reach and the motion of gas. Tidal forces stretch out great streams of stars and dust. Waves of compression sweep through gas clouds and trigger bursts of star formation that can burn through much of a galaxy's fuel in tens of millions of years. The Milky Way and the Andromeda Galaxy are already on approach. Andromeda sits about 2.5 million light-years away and is closing at over 100 kilometers per second. In roughly 4 billion years, they will make their first close pass. the two disks will warp and pull out tails. After several passes and energy losses to gravity, the pair should settle into a single, larger system often nicknamed Milkomeda. The Sun is likely to keep shining throughout, moved to a new orbit, but avoiding direct stellar impacts, to future skies on a calm world. Andromeda would grow from a faint smudge to a broad band before the structures mix. Between galaxies, space is not empty. A thin, hot gas, called the warm-hot intergalactic medium, fills much of the volume. Its temperature ranges from about 100,000 to 10 million kelvins. It is so diffuse that it gives little light, but in total, it holds more ordinary matter than all the stars in all galaxies combined. Some of this gas never fell into galaxies. Some was blown out by supernovae and by outflows from active black holes. Over time, the medium acts as both a source and a sink. Galaxies draw from it as gas cools and slides inward. Galaxies also return mass and energy to it through winds and jets. Detecting this medium is hard. It leaves faint fingerprints by absorbing specific ultraviolet wavelengths from light coming to us from a bright, more distant source, such as a quasar. In places where gravity compresses it, the gas can glow in soft X-rays that modern space telescopes can map. On even larger scales, galaxies gather into groups and clusters, and those into superclusters. The Milky Way sits in the local group with about 80 known members, including Andromeda and the Triangulum Galaxy. The local group lies on the outskirts of the Virgo supercluster, roughly 110 million light-years across, with the Virgo cluster near its center and thousands of galaxies bound or semi-bound within. Flow patterns traced by the motions of many galaxies reveal a still larger structure named Laniakea, Hawaiian for immeasurable heaven. Laniakea spans about 520 million light-years and contains on the order of 100,000 galaxies, spread along broad streams that drain toward massive attractors. Beyond that scale, superclusters link into the cosmic web, filaments, hundreds of millions of light-years long, knotted at rich clusters and split by giant voids. One of the largest known features is the Hercules Corona Borealis Great Wall, a chain of galaxy clusters stretching roughly 10 billion light-years. Such numbers point to scales so large that light itself takes most of cosmic history to cross them. The pattern of this web traces its roots to tiny ripples present in the first instance. Quantum fluctuations during an early burst of rapid expansion called inflation were stretched to macroscopic size. After inflation ended, gravity began to amplify those small differences. Dark matter, which does not feel light, clumped first and laid down the skeleton of filaments and nodes. Ordinary matter later fell into those dark wells, cooled, and formed stars and galaxies where the wells were deepest. Where filaments cross, matter piled up into clusters. Where little mass was present, voids grew emptier as material flowed out toward denser regions. Large computer simulations that include these ingredients reproduce the web in detail, showing streams, mergers, and the steady buildup of structures over billions of years. The central engines inside galaxies link these huge scales to very small ones. Near a black hole's event horizon, only millions of kilometers across, gravity is so strong that not even light can escape. Just outside that horizon, orbital speeds reach a significant fraction of light speed, and magnetic fields can twist and reconnect in complex ways. Small changes in the rate of inflow can turn a quiet center into a brilliant quasar. The radiation and jets then press outward on gas across thousands or millions of light-years. In clusters, We see clear bubbles in hot gas where black hole jets have pushed material aside. Those bubbles rise like hot spots in a fluid and help keep the cluster gas from cooling too fast. In calmer galaxies, a black hole that feeds at a slow rate can still heat its surroundings and limit star formation, adding to the tight link between black hole mass and bulge properties. The tie between tiny and huge shows up in numbers measured across many systems. The mass of a central black hole relates not only to bulge mass, but also to the random speeds of stars in the bulge, a relation called the M-sigma connection. As gas builds up at the center, stars form and black holes gain mass. When the black hole crosses a certain activity threshold, its energy and momentum push back. Gas is driven out or heated. Star formation drops. Growth slows until the inflow and the feedback balance. The exact chain can differ from galaxy to galaxy. Some grow by steady gas inflow, others by mergers, but the end result clusters around the same set of ratios. During mergers, black holes can also merge. As two galaxies combine, their central black holes sink toward the common center through dynamical friction, gravitational tugs on background stars and gas that drain orbital energy. At close range, the pair forms a tight binary, and in the end, coalesces, sending out a burst of gravitational waves. Space-based gravitational wave observatories, planned for the next decades, are designed to detect such slow, heavy waves. On smaller scales, ground-based detectors already listen for the higher frequency waves from merging stellar mass black holes and neutron stars. Together, these tools will map how black holes of many sizes have grown across time. While black holes draw attention, the bulk of visible matter sits in stars spread across galaxy disks and halos. A star is a stable nuclear furnace balanced by gravity. In its core, hydrogen fuses into helium, releasing energy that supports the star against collapse. When hydrogen runs low, heavier elements form in stages for stars with enough mass, building up the chemical richness needed for rocky planets and, eventually, for life chemistry. The rate at which a galaxy forms stars depends on its gas supply, its dark halo's pull, and the feedback it has experienced. Spiral galaxies often maintain a steady pace, forming a few suns per year. Starburst galaxies triggered by mergers can spike to hundreds of suns per year, but such bursts are short-lived because gas gets used up or blown out. The intergalactic medium and the halos around galaxies act as the pipelines in this cycle. Cold streams flow along filaments into halos. Some gas settles into rotating disks and makes new stars. Some is heated by supernovae or by black hole activity and joins a hot halo that can take a long time to cool and return. The balance between inflow, star formation, and outflow sets a galaxy's path. Even dwarf galaxies, which are small and faint, participate. They are common, sensitive to feedback, and can be disrupted by tides when passing close to larger neighbors. Their remains form long stellar streams that wrap around larger galaxies. Mapping these streams helps scientists read the hidden shape of the surrounding dark matter halo. The Milky Way shows examples of each process. Its central black hole is quiet most of the time, flaring only at low levels. The disk forms a few new stars each year from gas that flows in and recycles. Satellite galaxies like the Large and Small Magellanic Clouds orbit nearby, pulling out gas bridges and tails. In the distant past, the Milky Way has swallowed smaller galaxies. Their debris is seen today as arcs of stars. The halo contains globular clusters, old, dense star groups that likely formed early and now trace the outer potential well. All of these features sit within a dark matter halo that extends far beyond the visible disk. Across the local group, Andromeda shows a brighter bulge and signs of past mergers. In the Virgo cluster, the intra-cluster gas glows in X-rays, and the galaxies move in a deep potential, well made mostly of dark matter. Farther out, along filaments feeding the cluster, galaxies fall inward, stretch, and sometimes break into smaller pieces before reassembling. The shapes we image are snapshots in long stories, driven by gravity and cooled by radiation. Even the thin intergalactic gas leaves a record that can be read. Light from a bright quasar passes through many clouds on its way to Earth. Each cloud absorbs specific wavelengths set by the atoms and ions in it. The result is a forest of narrow absorption lines. By measuring their positions and strengths, astronomers map the density, temperature, and motion of the gas far from any galaxy. In places where many structures overlap, the gas is compressed and heated enough to glow. X-ray and ultraviolet observatories measure that glow and help close the census of ordinary matter. How much sits in stars, how much in gas inside galaxies, and how much in the warm, hot medium outside. The cosmic web extends beyond what we can see. The observable universe is limited by the distance light has been able to travel since the Big Bang. Structures do not end at that boundary. They simply lie beyond our horizon. The part we can map already shows self-similar patterns, filaments, nodes, and voids, repeating at larger scales. Within that framework, galaxies are the bright beads, black holes are the compact engines, and stars are the factories that build the elements. Each layer depends on the others. Dark matter sets the stage. Gas and radiation write the visible lines. Gravity ties scenes together across time and distance. Stars grow out of cold, dense gas in the interstellar medium. In some regions, gravity becomes stronger than the push of heat, and a giant cloud starts to contract. As it falls inward, it breaks into smaller clumps. Each clump can form one star or a small system of two or more. While the gas falls, it heats up because gravitational energy turns into thermal energy. Dust and gas radiate some heat away, so the collapse continues. In the center, the temperature keeps rising. When the core reaches roughly 10 million kelvins, hydrogen nuclei begin to fuse into helium. That fusion releases energy, builds pressure, and stops the collapse. A new star has reached the main sequence, the long, steady phase when it burns hydrogen in its core. A star's mass sets its path. Low-mass stars live slowly. A star like the Sun will spend about 10 billion years as a main sequence star. As hydrogen in the core runs out, fusion moves to a shell around an inert helium core. The outer layers expand and cool, and the star becomes a red giant, hundreds of times larger than before. In the compact core, the temperature climbs to about 100 million kelvins. Helium fusion starts and makes carbon and oxygen. For a time, the star is stable again, with a helium-burning core and hydrogen-burning shell. When helium is spent, the outer layers drift away into space as a thin, glowing shell called a planetary nebula. The core that remains is a white dwarf, about the size of Earth, but with roughly half the Sun's mass. No new fusion occurs inside it. It shines because it is hot, and over trillions of years it cools and fades. In a future far beyond the current age of the universe, such white dwarfs will become black dwarfs, cold remnants that no longer give off visible light. Massive stars take a different, faster road. A star with 20 solar masses lasts only about 10 million years on the main sequence. Its higher core pressure and temperature mean it burns fuel quickly. After hydrogen, it fuses helium into carbon and oxygen. Then in stages, it burns carbon to neon and magnesium, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon to iron and nickel. Each stage goes faster than the last because the energy gained per reaction gets smaller, so the star must burn fuel at a higher rate to hold itself up. The silicon stage is so short that it can last only about a day before the core becomes iron-rich. Iron marks a wall. Fusing iron does not release energy, it uses it. When the iron core grows to about 1.4 times the Sun's mass, the Chandrasekhar limit electron pressure can no longer support it. Collapse begins and races ahead in less than a second. Electrons combine with protons to make neutrons, and a flood of neutrinos carries away most of the released energy. The core shrinks from about Earth size to a sphere roughly 20 kilometers across. At nuclear density, about 10–14 grams per cubic centimeter neutron pressure, and nuclear forces stiffen the matter. The inner core stops. The infalling outer core slams into it, and a shock wave forms and moves outward. With help from neutrinos depositing energy, the shock breaks through the star and ejects the outer layers at thousands of kilometers per second. For a short time, the supernova can outshine an entire galaxy. In that blast, nuclei heavier than iron are made by rapid neutron capture, the R process. Gold, platinum, uranium, and many other heavy elements are created in this brief, extreme setting. The explosion spreads new elements across space, mixing them into the interstellar medium. Later, clouds pick up these atoms, and new stars and planets inherit them. The basic chemistry of rocks, oceans, atmospheres, and life traces back to these events. Every atom in the body heavier than helium was forged in a star, either in steady fusion or in the fast neutron capture of a supernova or a neutron star merger. Not every massive star leaves the same kind of remnant. The most massive may be destroyed completely in a pair instability supernova, with no core left behind. Others leave a neutron star, a city-size object, with the mass of the Sun or more, packed so tightly that a teaspoon of its matter would weigh more than the total mass of all humans. A typical neutron star has about 1.4 solar masses within a diameter of about 20 kilometers. Surface gravity is about 200 billion times Earth's. If you dropped an object from 1 meter, and if air did not slow it, it would hit in a millionth of a second at a speed of several million kilometers per hour. The matter inside is still beyond full understanding. The outer crust likely holds a lattice of atomic nuclei, soaked in a sea of electrons squeezed into a degenerate state. Deeper in, free neutrons appear. In the inner crust, nuclei coexist with a neutron fluid and may arrange into odd shapes, nicknamed nuclear pasta. The core may contain neutrons, protons, and electrons in exotic states. Some models allow particles with strange quarks, called hyperons. Others suggest a transition to deconfined quark matter, where quarks and gluons are no longer bound into individual nucleons. In that case, the innermost region could be a quark-gluon soup. A more extreme idea is strange quark matter, where up, down, and strange quarks form a stable phase. A star made mostly of such matter would be even denser. Neutron stars also carry record magnetic fields. Typical fields can reach 1 trillion times Earth's. Magnetars neutron stars with the strongest fields, up to about 1 quadrillion Gauss, store huge magnetic energy. Their crusts are rigid. Stress can build until a starquake cracks the surface. The sudden rearrangement unleashes bursts of X-rays and gamma rays that we can detect across the galaxy. Many neutron stars spin very fast. When a core collapses, spin speeds up, like a skater pulling in their arms. Newborn neutron stars can rotate many times per second. In some, a beam of radio waves, X-rays, or gamma rays sweeps through space from the magnetic poles. If the beam crosses Earth, our telescopes record regular flashes. We call such objects pulsars. The first pulsar was found in 1967 by Jocelyn Bell Burnell while she was a graduate student. The pulsars were so regular that the source was briefly labeled LGM1 for Little Green Men before the natural explanation was worked out. Pulsar timing is so precise that arrays of millisecond pulsars scattered across the sky act as a giant detector for very low-frequency gravitational waves. As ripples in space-time pass between Earth and the pulsars, the arrival times shift by tiny amounts. By comparing many pulsars, astronomers can pick out a common signal from the noise. This method probes waves made by pairs of supermassive black holes spiraling together over millions of years. Between and around stars lies the interstellar medium, a patchwork of gas, dust, plasma, and high-energy particles. It is not uniform. In the coldest parts, called molecular clouds, temperatures are only a few degrees above absolute zero, and densities are high enough for molecules like H2 and CO to form. Star formation starts there. Much of the disk of a galaxy contains warm, neutral hydrogen at thousands of degrees, more diffuse but widespread. Near hot young stars, ultraviolet light strips electrons from atoms and creates H2 regions, zones of ionized gas that glow in visible light. Supernova shocks heat pockets of gas to millions of degrees, filling cavities with hot plasma. Dust grains, built from carbon, silicates, and ices, absorb and scatter starlight and glow in the infrared. This mix cycles mass and metals from one phase to another as stars form, shine, and die. Magnetic fields thread the interstellar medium. Their typical strength is a few microgauss, about 1 million times weaker than Earth's field, but they extend over huge distances. The fields guide charged particles, including cosmic rays, and help support gas against gravity on some scales. They also influence how clouds collapse. Gas often falls along field lines more easily than across them, shaping the filaments seen in star-forming regions. Turbulence, driven by supernovae and by the motion of gas in galactic rotation, tangles the fields and stirs the medium. Over time, galaxy-scale dynamos can amplify weak seed fields into the large-scale patterns seen today. New stars inject energy and momentum back into their surroundings. Stellar winds, radiation pressure, and supernovae carve bubbles and shells in the gas. These feedback effects can clear away gas from a region, shut down star formation locally, or compress neighboring clouds and trigger fresh collapse. In galaxies with rapid star birth, many supernovae can cooperate to launch galactic winds that flow out of the disk into the halo and beyond, carrying metals into the intergalactic medium. The balance of gravity pulling in and feedback pushing out helps set how fast a galaxy turns gas into stars over time. Some stars end their lives more quietly, but still leave strong marks. White dwarfs in tight binaries can pull gas from a companion. If enough matter builds up, the white dwarf may reach a critical mass and ignite runaway fusion on its surface, producing a nova, or, if conditions allow, ignite carbon in the core and explode as a Type Ia supernova. Type Ia events are valuable because their peak brightness can be standardized. By comparing apparent brightness with known intrinsic brightness, astronomers estimate distances across large scales. These measurements, combined with redshift, helped reveal the accelerating expansion of the universe. In neutron star binaries, close orbits can lead to mergers. When two neutron stars spiral together, they emit gravitational waves. In 2017, observatories recorded such a wave, along with a burst of light across the spectrum. The event showed that neutron star mergers create heavy elements through rapid neutron capture, and that they power a transient glow called a kilonova. That glow fades over days as newly made radioactive elements decay and heat the ejector. This discovery connected the birth of gold and other heavy elements directly to compact mergers. The full life cycle of matter in a galaxy runs through these stages again and again. Gas cools and collapses to make stars. Massive stars explode and return heavy elements to space. Lightweight stars shed envelopes gently and add carbon and nitrogen to the mix. Dust forms in outflows and in supernova ejecta, grows in cold clouds, and later is destroyed in shocks. Magnetic fields and turbulence shape the clouds. Cosmic rays thread through and add extra pressure. Over millions to billions of years, this cycle builds the materials needed for rocky worlds, atmospheres, oceans, and the chemistry that can support life. Tools across the spectrum help map each part. Radio telescopes trace cold hydrogen and molecules. Infrared observatories see dust and the faint glow of cool stars. Optical telescopes resolve star clusters and measure the motions and compositions of stars. Ultraviolet instruments pick up hot young stars and gas they ionize. X-ray observatories chart hot plasma and the areas around compact objects. Gravitational wave detectors add a new channel that reads the motion of massive bodies directly. Together, these data describe how stars are born, how they live and die, and how their feedback shapes the larger systems that contain them. From star-forming clouds to neutron stars, from gentle planetary nebulae to powerful supernovae, the processes are tied to basic physics: gravity, nuclear fusion, radiation, magnetism, and quantum rules that set the behavior of dense matter and light. The same principles that hold a star steady for billions of years also drive the fast events that end a star's life. The materials that build planets and bodies come from those events. The interstellar medium carries the products onward, and the cycle starts again in the next cloud.